Hey guys, this is Mrs. Harbin, and this is the end of Chapter 3. Today we're going to be looking at Section 3.8, which is all about using equations to solve mixture problems. Just like our distance problems in the previous lesson, we're going to be creating charts, figuring out what we know and what we're trying to find out, and using those charts to help us find that missing information. Our biblical integration for our unit is this: Jesus set the highest standard for us to live up to by sacrificing all in service to his Father. We should be willing to do no less in our commitment to working for him. Our lesson objective for today is this: you, the student, will solve problems involving mixtures. Now, mixture problems can be difficult because they involve the combination of different substances. Think about a cereal, for example, like Lucky Charms. You've got the cereal piece mixed with the marshmallow piece, or Raisin Bran. You've got the flakes mixed with the raisins. So cereals are a good kind of mental picture for what we're looking at when we're looking at mixtures, because they involve the combination of different substances. Making a table is going to be what's most helpful to us when we're trying to solve mixture problems. When solving mixture problems, we want to do these things. First, we want to read the problem carefully. We'll create a chart that helps us keep track of what we already know, and we'll use one variable, to represent the information that we don't know. We'll plan a strategy then. After filling out the chart, we'll look at what we know and what we're trying to find out and see what equation we can write using the information from our chart to solve for the variable. We then will solve our equation again to solve for that variable. And finally, we'll plug that variable back into the original equation to check our work. So let's take a look at an example. This comes from Example 1 in your book, page 135. And we're going to be looking at a mixture of bushels of corn and barley. When we measure agricultural products like corn and barley, we're measuring it in bushels. And we're going to look at the number of bushels, we're going to look at the price per bushel, and we're going to look at the total cost. We're then going to create a mixture of corn and barley, and that mixture is also going to have a price per bushel and a total cost as well. So let's take a look at our chart. So we've created this chart. We've got the two things that we're mixing together here, the corn and the barley. And then we have our final product, the mix, listed here at the bottom. So our charts will always be set up this way, with things that we're mixing up on the top and our total mixture down here at the bottom. And then we have the different pieces of information. We're going to have the number of bushels, the price per bushel, and our total cost. The number of bushels, so I'm going to put a B for bushels, times the price per bushel is going to equal our total cost. So let's say we had 2 bushels and they're each $2 a piece. 2 times 2, $4. So you guys can hopefully see the logic in that. Based on the example, let's fill in what we know. We know that the price per bushel for corn is $3.80. And we know the price per bushel for barley is $2.60. And we know that once we mix it together, our new price per bushel is $3. Now, just looking at that, think for yourself for a minute. Is that $3? Is that closer to $2.60, or is it closer to $3.80? Well, it's closer to $2.60. It's only 40 cents away. It's 80 cents away from the price per bushel for corn. What that tells me is that my mixture is probably going to have more of the barley than the corn. Since the barley is cheaper and my price is closer to the barley price than it is to the corn price, my final mixture will have more barley than corn. Okay, I also know that my mixture has a total number of 150 bushels. What I don't know is how many bushels that is of corn and how much of it is barley. Again, I can logically look at the price per bushel and think to myself it should have more barley, but I don't know the exact numbers. So I'm going to use C to represent corn. And because I can only use one variable, I'm going to have barley equal to 150 minus C. If there are 150 bushels and C of those bushels are corn, then the leftovers, 150 minus C, must be the barley. To write the total cost, I know that B times P equals my total cost. So I'm going to take these first two columns here and write an expression for my total cost. So my total cost for corn is 3.8 times C. And my total cost for the barley is 2.6 times 150 minus C. And I know I'm told in the problem that the total cost for my mix is $450. Now I've got my chart completely filled out, and so I'm going to look at what equations I can write down to help me solve for the variable. Now a lot of times when we're doing a mixture problem, what we're going to end up doing is looking at this last column, and usually we'll add these together. The cost of the corn plus the cost of the barley equals the cost of my total mixture. Now that doesn't happen all the time, but it will happen very frequently, and we'll be able to solve for C that way. So let's go ahead and write that equation. 3.8C plus 2.6 times 150 minus C equals 450. We'll then distribute to get rid of the parentheses, combine like terms on the left side, and move our 390, subtract 390 from this side, and subtract 390 from this side, and that gives us 1.2C equals 60. We'll then divide both sides by 1.2, so that I'm left with C equals 50. If we go back into our chart then and we plug that back in, we'll see that we have 50 bushels of corn and 150 minus 50 bushels of barley, which is 100 bushels of barley. So just like I predicted, before we even did any kind of equations, I do have more barley than corn, and I know that because the price of my mixture was closer to barley's price than to corn's price. All right, let's try a second example again from our book. This one is about nickel, a nickel mixture. And pure nickel, by definition, is 100% nickel. Pounds of metal times the percent of nickel equals how many pounds of nickel. So when we mix nickel with other metals, we can still go back and figure out how much nickel is in that mixture. An alloy is a combination of nickel silver and pure nickel. So let's go ahead and set up our chart. P is going to represent the number of pounds of the pure nickel in our chart here. So we're mixing two things, nickel silver and pure nickel, and our combined mixture, our total here, will be what's called an alloy. We're told that nickel silver is 0.15% nickel, and pure nickel is 100% nickel, and we represent 100% with a 1. Our alloy is going to be 0.2% or 0.2 nickel, so 20% nickel. Now, looking at that logically, what that tells me, 20% is much closer to 15 than it is to 100. So our mixture is going to be mostly nickel silver with a little bit of pure nickel mixed in. I don't know the exact number unless I set up an equation and solve it, but logically, I should know that I'm going to have more nickel silver than pure nickel. If I do the math and that doesn't come out that way, then I know that I can go back and check it to make sure that I have not messed something up somewhere. All right, when we look at the pounds of metal, we know that we have 70 pounds of nickel silver. We don't know how many pounds we're going to have of pure nickel. And our alloy will be represented as 70 plus P. Again, we can only use one variable, so I have to think of a way to represent these amounts using only one variable. Our pounds of nickel then would be 70 times 0.15 and P times 1.0, which is 1P. And our alloy then would be these two things added together. 0.15 times 7 plus 1P. We're going to write that as an equation, and we get 0.157 plus 1P equals 0.2 times 70 plus P. Okay. We got this 0.2 times 70 plus P from these two things added together right here. This plus this. Sorry, this times this, my mistake, equals that. We did that for all of these. Pounds of metal times percent of nickel equals pounds of nickel. There we go. And we know that these two things equal our total here, and that's where that equation comes from. We're then going to use algebra to distribute and get rid of the parentheses, and then we'll start combining our like terms. When all of our like terms have been combined, we end up with 80P equals 350. Now, I did skip a step here. If you would like to get rid of the decimals so that you're not dealing with decimals, you can multiply everything by 100. And that will move all of our decimals over 2 places. And also we'll add a 100 in front of the p, because 100 times 1 is 100p. You don't have to do that. You can deal with decimals, but if you want to get rid of the decimals, that's the way that you do it. Okay, we're going to divide both sides here, and we get p equals 4.375 pounds of pure nickel. If we want to go back and look then, 4.375 pounds of pure nickel, let's see if our prediction was correct. Okay, we said we would have much more nickel silver than pure nickel, and we had 70 pounds of nickel silver and only 4.3 pounds of pure nickel. So we did have much more nickel silver than pure nickel in our alloy. All right, so today we did these things. We solved problems involving mixtures. We read the problem carefully. We created a chart to determine what we know. We made sure our chart was written using only one variable, and that each of our unknowns could be expressed in terms of that one variable. We then create an equation using our variable and solve the equation for the variable. Once we were done, we checked to make sure our answer was logical and correct. If you guys have any questions, be sure to write those down and bring those with you next class.